Swayam Prabha. Digital India. Educated India.
Hello everyone. Today is the second lecture of this week. In the first lecture we have seen how to construct shape function for the most basic element in two dimension, that is three-noded triangle, constant strain triangle. And what we did there while constructing the shape function, we first started with a polynomial approximation, and in that approximation we have certain constants, and then we impose a condition that the approximation should be such that it interpolates the nodal values, interpolates the primary variable at the nodes. And with this condition, we determine those constants, and eventually we have the shape function. And because of this condition, this imposition of this constraint, the final shape function has interpolation property. We'll be doing the similar exercise for other different kinds of element in two dimension. But before that, there are few issues that require some discussion. For instance, we start with a polynomial approximation. So the question may come that what should be the order of that approximation? How many terms to be taken in that approximation? What are the terms to be taken in the approximation? The approximation we are doing at the element level. But what happens to the approximation globally? If we see we approximate the field variable at the element level, and then if we see how over the entire domain with this small patch, every patch we have a local level approximation, element wise approximation. But when we combine them together and look at the entire domain, then how this approximation, how better is that approximation? Those things we will discuss today. So today's topic is continuity and completeness. Now, continuity is a word you all are familiar with. A function f defined over a domain omega is said to be continuous. Is called Cn function if its derivative of order j, when j, all the derivatives up to n exist and are continuous function in the entire domain. For an example, this is some representative function. If you take the blue one, this function is C naught function, okay, and then the red one, this function is C minus 1 function. You see this function, the blue one is just the continuous function, okay. Now C minus 1, it is not even continuous. Forget about differentiability, it is not even continuous function. And then green one, it is C1 function. So whether it is C1 or not, that for that we need the expression of the function. But just now, as I said, if we compare this function with this one and this one, this is C1 function, okay. And this C0, C1, these are the functions that we'll be dealing with in finite element method. One important note, whether it is C minus 1 or C0 or C1, we'll come to this, but just to make a statement now, by looking at this figure, whether it is C minus 1, C0 or C1, all these functions are integrable function. If we integrate it, then this integration over a domain is finite, right? That is important, okay. So let's talk about global continuity. Global continuity, first let's talk about local continuity. Element level approximation is this. We have seen, at least for one dimension case, how to calculate phi at the element level, and these are the degrees of freedom at the element level, and phi I are the shape functions within the element, okay. For instance, if we we have seen for 2-node bar element, these are the shape functions. For 3-node bar element, this is shape function. For 2-node beam element, these are the shape functions. So these shape functions, what they do, they approximate the function over an element. Okay. Now let us see the global approximation. Global approximation is this. Suppose ux is the global variable and uy are the global degrees of freedom, and I is equal to 1 to n, capital N, when the capital N is the total number of nodes we have in the system, and small n is the number of nodes we have within the element, and this phi is the global shape function. Global shape function are essentially all the shape function at the element level. The combination of these element level shape functions will give you the global shape function, right? Now let's see that. Now before that, one important thing. So whenever when we say whether function is C0 continuous or C1 continuous, what is the level of continuity of a function we have? Now a function may be combination of several. For instance, if phi I in this case is a combination of all these phi I. So it could be a combination of many functions. Then the continuity of this entire function will be governed by the lowest continuity in that link, in that summation. Okay. Now let's take two element. One is 2-node bar element and 3-node bar element. These are the shape function. Now what we are interested now is what happens at the junction of two elements. Within the element we have seen the how to construct shape function and how to approximate a function, but now we are interested to see what happens at the junction of two elements, and similarly junction of all the elements. Okay. Now let's take two elements. This is one and this is one in one dimension. Suppose these two elements are 2-node bar element. This is the common node between this element and this say element number E1 and element number E2. This is the common node. Now let us plot the shape function and their first derivative in this case. So what are the shape functions plotted? Now for E1, the E2 is shown here. This is phi 2 is shown here, and for E2, for this element only phi 1 is shown. Okay, so this is how the shape function looks. So at this node, because if we look at E1, the shape function corresponding to this node is equal to phi 2, and if we look at E2, shape function corresponding to the common node is equal to phi 1. So if we look at as a whole, taking the contribution from both the element E1 and E2 and see the global shape function, look like this. That is associated with node, this common node. And if we plot the derivative, this is the derivative of the shape function. Okay. Now we see that this shape function at the inter-element boundary at the junction, this shape function is continuous, but it's not differentiable at this point. So this is a C0 function. Now let us take the 3-node bar element. Now in 3-node bar element, if you recall, our shape function within the element, shape function was quadratic. Right. Now there are 3 shape functions, but all shape functions are not plotted here. So what shape functions are plotted? This for this element, this is E1 and this is E2. So for E1, from E1, the shape functions are plotted is phi 3. This is, and from E2, shape function plotted is phi 1. Okay. The idea here is to make a point. Ideally, I could have plotted all the shape functions, but in that case, this figure would not have been very clear. That's why only these two shape functions are plotted here. Now, if we see, this is the function, the global shape function for this, and then this is the derivative, and we see that this function is also C0 continuous. But look for this element, 2-node bar element, our approximation within the element was linear. In 3-node bar element, our approximation within the element was quadratic. That's absolutely fine, but when we look at the inter-element boundary, at the point where two elements connect, at that point these functions are all, the shape functions are all C not continuous, C0 continuity we have, right? And this is not a surprise, because again, if you recall, how did we compute the shape function, whether it is 2-node bar element or 3-node bar element? The only condition we invoked was to interpolate the primary variable, and C naught continuity is enough to satisfy that, right? Now let's take the next is 2-noded beam element, and these are the shape functions, and the shape functions are plotted like this. Not all shape functions plotted from element number, this is okay, this is element number 1, this is element number 2. Now from element number 1, 5, 4, this is plotted, and from element number 1, this is plotted. Okay, these two plotted. Now this is phi x, the phi x is continuous, and then this is the derivative of, so this phi is global shape function at the common node. Now this is the first derivative and this is the second derivative. Okay, now we see that first derivative is continuous at the inter-element boundary at the node connecting two elements, but the second derivative is not continuous. So this is C1 continuity. Again, this is not a surprise, because if you recall, when we constructed shape function, we could not, the philosophy we used for constructing shape function in case of bar element and in case of beam element were different. Okay, so when we constructed shape function for B element, it was not only the primary variable, we also interpolated its derivative, because we wanted to have the compatibility or continuity in the slope as well. And that is the reason why the first derivative at the inter-element boundary, the first derivative is also continuous. Okay, so this is a global approximation. Now, so let's take our previous case. Let's take this previous case. We have seen our global approximation is C0 approximation. Okay, now C0 approximation. Now, if you recall, in our in the weak formulation, we had a term like integration of dw dx du dx, okay, and then d omega. This is for quadratic, this is for second order differential equation in 1D, and then when we write it the quadratic functional, in the quadratic function what we have is du dx whole square. I am not writing the entire term, this is the term present in the weak form, right? Now a shape function is C naught continuous, we have seen it. Now if shape function is C naught continuous, if we differentiate it, in the derivatives we have this jump. Just now we had seen the similar kind of jump in this case, jump. Okay. Now similar kind of jump we have here is. Now, but what matters, this is not a problem with us, because what matters here is whether, now du dx has jump, this jump. Okay. Now what matters here is whether these are integrable or not. See, these at the end we have to perform this integration. So this should be, the function should be integrable. Even the function has this jump, this should be integrable. Okay, not just the function, the square of this should be integrable. Okay, so square integrability is a important criteria for this. Okay, now, and if we look from that, the minimum requirement is C naught continuous. Before we come to another aspect which is called completeness, let us see some of the sources in error, some sources of error in finite element finite element solution. Please note, this is not the discussion on the detailed account of different sources of error, their measures, the estimate. For that, we will see towards the end, probably last week, if we get some time, we can have that discussion. But just to set the context right, so that we can introduce completeness, we can look at completeness in a better perspective. Let us see some of the sources of error and what are the measures of those errors. One error is obvious, that is domain approximation error. Finite element method is essentially an approximation, right? So we seek for an approximation solution, and we do approximation at various levels. One of the approximation we do is the domain approximation. The idealization of the domain, approximation of the computational domain by elements. For instance, if you take these three cases, now actually the problem is we have a plate, then we have a circular cut like this, but then when you discretize this plate with a coarse element, you your domain, which was otherwise this, but your idealization is this. If we increase the number of element, then the approximation becomes slightly better, and further increase in element, approximation is even better. But this problem is not very relevant in one-dimensional cases. We will see two-dimensional problem, and in three-dimensional problem, this is an important source of error. Then another source of error is quadrature and finite arithmetic error. We have to do integration. We will see what the techniques for numerical integration in subsequent classes, and then eventually we have to write a program, we have to implement in a computer code. There we have some arithmetic the round of errors. These are some sources of error. Then another source of error, which is the important for us for today's discussion, is the approximation error. Then we approximate the solution over an element, right? And this approximation approximate a variable over an element. And how do we do this approximation? This approximation is this. Okay, suppose ui are the nodal values and uh is the finite element solution. So this is an approximation of the entire solution, and n is the this is the global approximation I am talking about, and phi I is the global shape function. So this is there will be some error in this solution. Okay, now let us see how to represent that error. What are the different measures we have for this error? So n is the total number of nodes, ui the global node at u are the global node I, and phi is the global shape function. Let us see different measures of error. Derivation of this we will not go into detail. There are different measures. One first measure is the maximum error. You have a solution, true solution, say u is the true solution, and uh is the finite element solution. So what is the maximum difference between u and uh over the domain? That is the error. Okay, that is one measure of error. This is another. Another error is called energy norm, or measure is called energy norm. Now look at this. M is the order of differential equation being solved. For instance, now, and then if M is the order of differential equation we have, then if you recall in the weak formulation, we have the differentiability requirement is M. If 2m is the order of differential equation. For quadratic, for a second order differential equation in the weak form, we have du dx term. In the fourth order equation, we have del 2u del x2 term. Now, this norm is defined. So m is the 2m is the order of the differential equation. Now, this is on the derivative of this variable, and the order of the derivative is same as we have in the weak formulation. So this this measure is defined on that. Now, if you recall, if we have du dx whole square term in a quadratic functional d omega, and if you put it in solid mechanics context, you will see that this is a measure of energy. Okay, that's why it is called energy norm. And another measure is the L2 norm, which is defined as this. Okay, the square of the difference give you the L2 norm. Now, for instance, suppose blue one is the true solution and the red one is the finite element solution. Now, the maximum difference between the true solution and finite element solution is this norm. Okay. Now, at every we look at different points wherever it is maximum. The maximum deviation between these u and uh is this, and this is how it is represented. Okay. And what is L2? L2 norm is which is this integrated over the entire domain, and which is essentially this is the L2 norm. The area you can see, shaded area you can see, that is the L2 norm. Okay. Now, another interesting result, again we will not go into the detail, will not derive it, but it is very important to understand the importance of completeness. See, finite element, one beauty of the beauty of finite element method is, before you actually apply finite element method for a problem, we can estimate the error, and this is an estimate of finite element error. And what it says that this is energy norm, u minus uh less than c h to the power p. So if you apply a finite element framework, develop a finite element framework where your element size is h and your degree of the polynomial you have in the approximation, the complete polynomials in the approximation is k, then the solution of finite element will converge with this rate. Okay, well, p will give you the rate of convergence. Now, by look at this, you can see that if you keep on reducing the element size h, you will get convergence, or if you keep on increasing p, you will get convergence. Okay. Now, what is important to take for our discussion today is this: if the finite element interpolation function phi I are complete polynomials of degree k, the error in the energy norm can be shown as this: the complete polynomials of degree k. And what is complete polynomial? The definition of completeness is it includes all lower order terms up to the highest order used. For instance, if you take a function like this, now highest order monomial we have in this, the degree, highest degree in this polynomial we have 4, but then all the terms below 4 do not exist in the, we have not taken that into this polynomial. For instance, where x cube term associated with x3, x to the power 3 is missing in this polynomial. So this, for this polynomial is complete only up to this. So we have a constant term, we have linear term, and we have quadratic term. Even though we have the fourth order term, but since we do not have cubic term, so the completeness of this polynomial cannot be taken as 4. Okay, so we can say that in this case the k is equal to 2. In this expression, k is equal to 2, right? So when we construct a safe function, so naturally at the convergence is an important thing. At the end of the day, when we apply finite element solution to get finite element method to get a solution, we should be sure that our solution is close to the true solution. Even if true solution we do not know, then also at least we should check the convergence, whether the results, if we keep on increasing the L number of element or order of element, whether it is converging to a value or not. Okay, so that's why how we can get convergence, this information is very important. Now with this, let us now understand what is the importance of complete polynomials. Now, so in one dimension case, we know that this is how it is quite straightforward, right? But in two dimension case, what are the terms to be taken in approximation so that our approximation is complete? and this is given by Pascal triangle. Now, what this Pascal triangle tells you, this is in 2 dimensions. Similarly, you can also draw a similar kind of thing in 3 dimension as well. Now, for constant term, this is constant term. If your approximation is linear, then we have to take all this term, means 1xy. This is for linear. If we want to take our approximation quadratic in the sense the complete quadratic, then this is our term, total 6 terms to be taken. And then if it is cubic, then all this term to be taken. This 4th order, all this term to be taken. Quintic, all this term to be taken. And similarly, you can go on increasing the order. So this is how we can be sure that our approximation is complete or not. Okay. But then requirement of completeness, this is an estimate, tells you that from this estimate we know that complete polynomials is important, and from this Pascal triangle we know that what are the terms to be taken in approximation so that the approximation is complete. But the question is, what happens if you take incomplete polynomial? Okay, let's do an exercise and convince ourselves, if we do not take complete polynomial, if we do not take certain terms in the approximation, then there will be a problem. Let's do that. So if you recall, we had already constructed the shape function for this element. Okay, 3-noded triangular element, and we have seen that for this your strains are constant, and that's why it is also called constant strain triangle. And if you recall, when we constructed this shape function, our approximation was c1 plus c2x plus c2 plus c3y. Okay, so the approximation has a constant term, then the linear in x, linear in y term. So if we look at Pascal's triangle, in that case our approximation, if you recall, our approximation was xy was c1 plus c or c0 c1x plus c2y, something like this. Okay, so this approximation is complete up to this degree 1, right? Now what we do is we'll take an approximation like this. Let us not take the constant term. Our approximation is x, then linear term we have taken, this term we have taken. So in Pascal triangle, if we again look at, so we have taken this term, and this term. Okay, but we have removed this term, the constant term. Okay, let's see what is the consequence. So this is the approximation. The next is this approximation needs to be satisfied at every nodal point. That is how the interpolation comes in, and this is the first equation we get, and similarly we will get other 2 equations. Now if we combine these equations, we know the coordinates and substitute the coordinates of all the nodes, we'll get an equation like this, and from this equation we get uxy is equal to xy. In this case it will be xy because that is our basis, xy, and then if we invert it, we get something like this, and then from there we get our shape function. And if we write our shape function, from this our shape functions will be this. This is for node 1, this is node 2, node 3. Let's see the properties of the shape function. That we know that it's Kronecker delta property, which is the interpolation property, then partition of unity property. With those properties this shape function satisfy or not. Let's first check Kronecker delta property. You can check if you substitute x and y any arbitrary nodal value, the coordinates, you will see that this shape function satisfy the Kronecker delta property. But there was no point in checking this property because this was the premise, this was the condition we invoked to determine c1, c2, all these constants, right? So it has to be there. That is how the constants were determined. Okay, so partition of property is a consequence of our constraint that we used to determine the constants. So this is how the shape functions look like. You can compare these shape functions with the shape functions we already obtained in the last class. Now, here comes the very interesting part. So, these are our shape functions, and then we know that if we add this shape function, it should satisfy, it should be 1, right? If we add this shape function, you see that this addition is not 1, it is a function of x and y. So, it doesn't satisfy Kronecker, doesn't satisfy partition of unity property. But then question is, what is the problem if it doesn't satisfy partition of unity property? We checked that when we took a complete polynomial, we took linear term, then when we took constant term, then linear in x, linear in y. The shape function that we obtained in the last class, those shape functions satisfy partition of unity, and it is a very, very important property. We will shortly see why. But this doesn't satisfy this. So this is the price that we have to pay for not taking the constant term in the approximation. But then what is the problem if it doesn't satisfy partition of unity property? Let's see what is the problem. Now suppose this is the element, and suppose this element is moving as a rigid body. Okay, so this element is moving as a rigid body. So when it moves as a rigid body, what happens? At every point, displacement will be same. So if we at this point, at this point, at this point, or any arbitrary point, our displacement will be same. So if the displacement is u here, displacement is u here, it is u here, or if we take any arbitrary point, there also it will be u. And what will be the strain in the body? The strain in the body will be 0. Okay. Now, how do we approximate the function, this field variable at any intermediate point, any arbitrary point within the element? We approximate through the shape functions. We know the nodal values, and then through the shape function we can get the value at any arbitrary point by this. So u at x and y is equal to summation of I, phi I and ui, right, when I is equal to 1 to n. So let us do that. U at x and y is equal to summation of I is equal to 1 to n. So phi I, and ui at all the node number 1, 2, 3, all the node, it is constant. So this is u. So this gives you u summation of I is equal to 1 to n phi I, and at any arbitrary point also it is u. So this clearly gives you I is equal to 1 to n summation of phi is equal to 1. This is our partition of unity property. So partition of unity property has a very important physical meaning. Meaning is this: now the shape function we constructed like this shape function doesn't satisfy this property. Means this shape function not even is not sufficient even to capture a rigid body motion. Forget about strains and all that, we will see whether it can capture or not, but just for a rigid body motion it is not able to capture. So that is how that when we construct a shape function, what are the terms to be taken in the polynomial, it is very important. Okay, so what we will stop here today. Next class what we do is, with this background, with this understanding that completeness is important, and continuity at the element level and the global level, how to look at continuity, with this understanding, next class what we do, we will take some other two-dimensional elements and derive shape functions for those elements. Thank you. See you in the next class.